Okay, I've started recording now. Very good. Good morning. Um, Today is our last day on motion tracking. Um, so the plan for today is quick recap of what we did so far and look at a number of applications of hidden Markov models. One in motion tracking, which is arm gesture recognition, which we'll see for the bulk of today's lecture. But we'll also look at applications, other applications such as autocorrect, auto edit, as well as a little bit quick glimpse into speech recognition. Everywhere hidden Markov models are useful. And towards the end of the class, time permitting, I want to kind of give you high level intuitions of additional popular algorithms that are built on top of hidden Markov models, namely simultaneous localization and mapping, SLAM, which your Roomba robots or your self-driving cars are kind of doing, as well as what is called particle filters, which is kind of the next step in state estimation. So that's the plan. Any questions thus far? Okay, good. As usual, thank you, Anthony, Utkarsh, Alex, for turning on the videos. Others, if you can turn on the videos, even for part of the class, it helps. Okay, thanks, Deep. Okay, so quick recap. I hope hidden Markov model is indeed not super easy, right? You have to it has to click. But once it clicks, I feel it becomes easy, and it's not. It looks a little bit intimidating, but it is not, right? In many cases, in many scenarios in math related topics, when you look at it, it feels like, whoa, there's so much of dense numbers flying around. But the pillars are usually few. You get a few things right, everything else falls in place. It's like yeah, it clicks. Okay. So I hope I hope this is intuitively clear to you and even mathematically clear to you. Remember, we were after this, the goal that we were after is there's this person who's walking. We have measurements about the person's location at every time. But the measurements are erroneous. We do not know if the measurements are completely believable. So we do not trust the measurements completely. But at the same time, we know some constraints or some aspects of that human's behavior. For example, we know that this person cannot walk as fast as a car, right? Or we know that when a person is walking forward, he or she is going to continue to walk forward with a high probability. So we have some motion model about the person's movement. And hidden Markov model says, come up with the person's trajectory that best agrees with the measurements as well as the motion model, right? And how do you model agreement? You model them as conditional probabilities, right? You say, this trajectory, given the measurements, what is that probability? This trajectory, given the motion model, what is that probability? And you then basically combine them under the Markovian assumption that everything the person is doing is a function of the current state. It does not matter what the previous state is, right? It's a function of the current state. Of course, if you take previous states into account, maybe the person is doing certain things as a function of the previous state. And if you can model them, maybe it becomes even better. But in many real world applications, just modeling as Markovian, which means the person is doing things as a function of the previous, of the current state, is good enough. Okay. So that intuition we basically formalized, and we said there are two components. We saw that there are two components when we try to do PSK given M1 through N. That breaks up into a forward component, which is the online or real-time one, and the backward component, which is the offline one. And then last class, we looked at both these forward and backward components. And lo and behold, it turned out to be a dynamic program, which is why we can do this reasonably efficiently. Okay. So if you want to estimate the state at Sk, which is the location of the user at time tk, that's the Sk random variable. If you want to figure out the probability of this Sk random variable, that turned out to be a dynamic program. And then we said for the backward part, which is mk plus 1 to n given Sk, this part is sometimes a little bit counterintuitive, but I hope you see that if I give you a sequence of grades of a student, and I tell you the grades till 12th grade, 12th standard, and then I say, what is the chance that the student went to UIUC? That's the forward part, where I tell you everything till 12th standard, till high school, and then I say, what is the chance Sk equals UIUC? You can do certain predictions. But then if I also tell you these are the college grades, what is the chance that the student is at UIUC or came from UIUC, right? Then you can say, then you can get even better understanding, because you know, oh, if the student came to UIUC, it must be a top quality student, and that must mean that his college grades are pretty strong. Therefore, the chances of coming from UIUC is stronger. Okay. So that's the backward part. And it also turned out that the backward part is also a dynamic program, except that it goes backwards. Bk is a function of bk plus 1. And we saw how we actually do the initialization of bk, because this initialization is not as easy as the previous initialization in the forward component. And then we put everything together. We said, okay, look, this is the state estimation at Sk. And that basically is this forward component, backward component, both are dynamic programs. Haha, we can basically find Sk for every value of k. And then there are more sophisticated techniques which says, okay, I'm not to find the person's trajectory. I'm not going to decode one state at a time, but I'm going to look at the whole vector of states, S1, S2, S3, S4, S5, all the way till Sn. That's the vector of states, and that's the trajectory. And we can ask the question, what is probability? Oh, here it is. What is probability of P S1 through N, which is the trajectory given M1 through N? And that can be done with what is called Viterbi decoding. So that is where we stopped last class. Questions?
I just wanted to clarify real quick. I know you went over this last class. The forward part is the likelihood, right? And the backward part is the posterior?
You tell me.
I'm guessing the backward, well, SK should be the entire space, right?
Exactly.
Okay.
So what is likelihood? What is posterior?
Posterior should have the sample space in the given part. So I'm guessing the forward part is the.
Wait. What? Okay. What is probability? Let's do it here. What is probability hypothesis given evidence? This is posterior or likelihood?
Oh God. I thought posterior was evidence given um, a hypothesis.
Other way.
Okay. I mixed it up. Thank you.
Yeah. So this is posterior. Okay. Another way of thinking about it is evidence given hypothesis, which is the likelihood, is often easy. This is like evidence given hypothesis is like, oh, my hypothesis is that this is the distribution. I have an evidence, which is this value. What is the probability? That's typically easy. But yeah, another way of saying is when your hypothesis is what you're looking for, that is the posterior. When your hypothesis is in the given part, that is the evidence, that is the likelihood. Okay, so this is posterior, this is likelihood. Adil, is that clear?
Yes, it is.
Other questions? Okay, if not, let's look at a few other fun applications. In fact, like I was saying the other day, there's just huge number of applications of HMMs. You use it every day, you just don't realize maybe. So let's look at a couple of them. Some other applications of HMM. This is an informal discussion. We are not going to do the math, but I think you'll understand the math completely now. So let's look at autocorrect. In smartphone keyboards. Okay, so here is a smartphone keyboard, and you are the keyboard team's manager, and someone has typed, and the locations of where that person's finger has touched are given by these 1, 2, 3, 4, 5. Your algorithm's job is to figure out what that person typed, and whatever that person typed, you want to put it up over here as suggestions. Right? Okay, guys, what did this person type? Let's see. How much can humans do HMMs in their head? I can see your brain doing. If it is W, then what other words are there? Okay, W followed by J. That's not possible. W followed by U. Maybe woo. What words start with woo? Right? You're actually doing a hidden Markov model, right? Because you have a sense of what word starts with woo, W-U, or what word start with W-I, we. W-J, not possible. W-H, not possible, right? This is what you're doing in your head. You have a dictionary of words in your head. That's your motion model, right? And you're trying to say, W, it could be W or it could be Q. Let's start with W and see what happens. Let's build up that tree. Then you can start with Q and say what happens, right? This is exactly what you're doing in your head. Okay, stare at it for a while and tell me what possible words should we give as suggestions. Whelm. Okay, so Deep has whelm. Good. Good. Is whelm a word? I know overwhelm is a word. Whelm is,
yeah, I Googled to make sure. Yeah, it is.
It is a word. Very good. What else? Actually, who can guess what I had in mind? While backspace. Okay, Utkarsh, not a bad one actually. W-H-I-L-E, and then you had a backspace. Okay, so she wants to write while. Maybe she wrote something else. Okay, maybe we can say while. What else? You still don't have what I had in mind. You're all starting with W. You're all your initial condition, you don't want to budge from W. You'd also budge from your initial condition, okay? Because you have to say, okay, the initial condition may also not be right. Oh, because I thought that if you start from Q, right, there's a strong chance you have U and you have your second location close to U. So that gives a strong motion model. Does that make sense, guys? Right? You want to go in that direction too, because if this was Q, then you're likely to see a U, and you do see something close to a U.
Quell?
Quell. One more. Quell, good. Okay. Now, if you assign this to M, this is L, which is pretty good, right? See, you all got that right? Because there's not too much movement that 4 can have. So you all put L in the 4th place, right? So that's good. M can go LJ, L followed by J hardly happens. L followed by K hardly happens, right? So 5, you can either put it back to L, you can put a backspace which Utkarsh did. Hey, what about that? That's possible. LM, there are some words that have LM. So Q, U, something, LM, right? This word, what can it be? This alphabet? Sorry, this letter?
It could be A, but that doesn't really make sense considering what it is.
But it might be that this 3 getting, here is a large error, right? That's a large error, but the rest of it fits very nicely, right? 5 cannot have J, cannot have K, can have double L, but can be M as well, okay? So I would say Quell is very, very nice. Quam is also very nice, or maybe a little bit less nice than Quell, because A has this thing, right? And now in your dictionary, if you look at all English language being used and you see that quam is used more often than quell, if you figure that, oh, quam is a more frequent word, that's part of your motion model too, right? On the other hand, if this article is about, if the keyboard software is seeing that you're writing about some protest, right? Well, you have to quell some protest or do something like that. Then you say, oh, okay, this is more likely to be quell, right? So you can your motion model can even give you information about, oh, this article seems to be about this topic. Given that topic, which word is more relevant, more probable? So you can do all of that underlying the keyboard, and then you give these suggestions. Okay, good. Very happy with your suggestions. Okay, so what exactly is the keyboard doing? The keyboard is saying P of M1 given S1, which is P of M1 equals location of 1, which essentially means that given S1 equals A, B, C, D, all the way till Z, blah, blah, blah. And Z, even after Z, actually, Z and all the backspaces and everything, 1, 2, 3, and everything. All the possible keys, that's S1. Okay, does this make sense? We use this very often in our hidden Markov model, right? I'm just converting that to what it means in the keyboard case. M1 is your measurement, is the location of 1. This is where your first finger tap has been measured. That given S1 is all possible keys. Adil, this is likelihood or posterior?
Why I gotta do this, Professor?
Say that again.
I think it's going to be, well, sample space is in the other one. So it's going to be like, oh my God.
You got it. You got it. You got it.
Okay, likelihood.
Yeah. Hey, this is easy, no? Why is this easy? Tell me, why is this easy? Okay, how do you calculate this? M1 equals probability of M1 equals location of 1 given S1 equals ABCD all the way till Z 1, 2, 3, blah, blah, blah. How do you get this?
Could it be from some kind of like data sheet or something? I know we talked about that for like the last, like it's kind of like talking about the sensor, I guess, error, I guess you would say.
But sure. But in this case, you can define something easier.
Maybe a Gaussian distribution.
Around what?
Around the letter location.
Correct, exactly.
Yeah.
Right? You can say the following. You can say, if my letter is Q, this is the Q key, okay? This is the Q, this is the Q key. I'm drawing that here. Okay. If the user intended to hit the Q key, actually, let's make it A. Maybe it's easier that way. If the user intended to hit the A key, I can define a Gaussian. Let's say he's going to hit this region with probability, with high probability. He's going to hit this region with lower, 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 and so on. So this is a 2D Gaussian. Right? I can define a 2D Gaussian around the key A. And if I know the mean and variance of that Gaussian, I can now say, okay, here is my Gaussian. I mean, imagine this is 2D, but I'm just drawing this is 1D. This is what my distance is to center of key A. Right? Because this value is your measurement M1. Right? Because that is basically you measured M1 over, your measurement M1 is over here. So from the center of, from your location of key tap to the center, this is your measurement. And from that, you have a distribution on the page. And from that distribution, you exactly know what that probability is. This value is this value. And this value tells you what the probability PM1 given S1 is. Right? Very simple. Now, how do you get this Gaussian? Guys, I think Utkarsh said Gaussian. Utkarsh, how do you know the mu and variance of this Gaussian?
Maybe empirical data.
Correct, exactly. You hire a bunch of people and you ask them, type these words. And they type. So you know what they're typing. And you see when they are going to type that A, where their fingers fall. Right? So you're in your empirical data, when you have this A, you get lots of people to type, maybe in Amazon Mechanical Turk, to type the same known words, and you see that their taps fall like that. Right? That's your distribution. You get that, you get your mu and your, you get your mu and your variance from that. You use that mu variance over here, and now you have this value. Very good. Okay, now the second part of this is, remember, HMM really has these two building blocks. Right? These are the real two building blocks in HMM. Everything is using this in interesting ways. So this S2 given S1, I can write as S2, sorry. Again, this is A, B, C, D all the way. Given S1 equals AB, but this one is likely Q, W, all the way. Right? Why did I write QW? Because this is likely to be QW or A. So A, Q, W are more likely. Right? But I don't want to make any conclusions right away. Right? I don't want to initially say that this must be A, B, or Q. I also want to be open to the fact that the first touch might have been E or S or even X, Z, I don't know. So I'm going to keep everything in the play, all the alphabet, all the letters in play. Right? I'm not going to eliminate them up front. Right? So now tell me, how do I compute this?
Will you use a transition matrix of some sort?
Correct. Where do I get the transition matrix from?
From like the dictionary, maybe?
Yeah.
Exactly. Exactly, right? You go to a dictionary from an English dictionary. What do? You go to the dictionary and you do what? I basically want A, B, Q, W, Z. You guys, I'm putting just dot, dot, dot. There are not enough columns, of course, columns and rows. I'm just saying this. Let me delete that. Let me put a U here, somewhere here. Yeah. I hope you don't get confused. I hope you see the point over here. You don't get confused. And what I want to say is Q and U, this is a high probability because after Q, there is U. And this is S1, this is S2. Okay, so how do you fill up this probability? How do you fill up this matrix now? You have an English dictionary. I give you an English dictionary. You have to fill up this matrix. What do you do?
You just basically record how many times each one occur and then divide by the total sum. Or like how often like one letter occurs after another. Exactly.
You take every word from the first word of the dictionary and you say the first letter, the first word has A followed by, is there any word that has two A's?
I have a friend whose name is AAMIR or Aaron. Aaron is two A's. Yeah.
No, but that's not in the dictionary though. Right? Eric, that's not in the names are not in dictionaries, right?
Yeah, true.
Yeah. Which is why when it comes to names, the keyword doesn't do very well.
Professor Aardvark is
Yes.
a word that starts with two A's.
What?
Aardvark.
I see.
Animal.
Okay. So there are a few words that has two A's, right? So you take that word, there are two A's. For AA, you do plus plus. Basically, you keep a counter for every, these are called bigrams. Okay. For every two letters, you keep a counter. Then you have AB, then you have AC, so on. Then you have BA, BB, so on. CA, CB, CC, so on. You keep a counter for every one of them. Now you go to the first word. Anthony, you said what was the word? Var? I don't know that word.
It's a AARDVACRCK. Yeah.
Something like that.
Sorry.
Oh, no problem. Yeah. Okay.
Yeah.
Thanks, Adil. Aardvark.
Yeah.
Okay.
Yeah.
So I see, okay, AA, I do +1 here. I do AR, I do +1 here. I do RD, I see RD, there is RA, RB, RC, RD, I do +1 here. Okay. I keep doing that for every word. Then what do? I sum up all those values for all those bigrams. I divide every value by their sum, by that total sum. Probability is 1. I put those ratio values, all less than 1, into this. Okay? That's how I built my state transition diagram.
Quick question.
Sure.
Do you, like, since you're creating the state transition diagram, do you have to worry about the, like, how frequent the words that you're taking these values from?
Exactly, right? It depends on, exactly right. Good question. So Utkarsh's question is, should aardvark get the same weight as the word politics? Right? Politics is a word that's getting very heavily used, right? Or sports, right? So this is where your model comes in. How much do you want to go? Right? You can go very far with this, right? You can say that, okay, I do not know what I do not have anything else other than a dictionary. Then that's the best you can do. But you can say, look, I'm going to take all Wikipedia articles as well. And from that, I'm going to count which word has how much frequency. Right? And if aardvark had very little frequency, it was mentioned two times in all Wikipedia articles, versus sports got mentioned 5,000 times, right? I'm going to multiply aardvark with 2 by 5,000 or 2 by 29,000 or whatever, how much ever word Wikipedia has. And I'm going to multiply sports with 5,000 by 35,000, if there are 35,000 words in Wikipedia, let's say. Right? So I can also add weights based on their frequency of occurrence. Right? If you know that I am typing an email, if the keyboard knows that I'm typing an email, the keyboard could potentially go and look at all my emails that I've typed in the past, create a histogram of all the words that I tend to use, and tune the weights based on that, right? So there's no end to how much domain knowledge you can bring and update your state transition matrix. Right? So clearly you can do very well.
I was also wondering, do you think in your dictionary you could also include commonly misspelled words?
Sure, totally. You can see, oh, from the past I have seen. So this is where machine learning is taking over, right? You can see that, oh, in the past I have seen that people forget to spell when they say Cornell, they oftentimes spell it with 2 L's. Right? You can bring that into your state transition and say, oh, whenever there is 2 L, they actually mean 1 L, and you put that in your suggestion. Very much, right? It's a open playground. The more that you can bring in, the better your model becomes. State transition probability diagram becomes.
Professor?
Yeah, Eric. Yeah.
How do you model after the backspaces and everything else that's not letters?
Say that again.
So we have a method to calculate the transition matrix for the letters, but how do we do it for backspaces and the other keys?
You don't have a model for backspaces. right? The only model you have is suppose someone has written QWEL and you suggest quell, right? But then this person does a backspace. So you know, okay, it's not L, it's QWE, right? And then you say, okay, QWE, what are the possibilities? And maybe Q is a possibility. So backspace may not be part of a model because backspace is saying that whatever I did, I'm undoing it. Does that make sense?
Yeah.
Also, this is the reason why it's difficult to predict when you write it in some other language other than English, right? I typed in mine in a different language, and of course then English, the keyboard thinks I'm typing gibberish, right? Also passwords, your keyboard cannot predict. Right? Password. That's why they say passwords do not have any kinds of substrings of English language in it. Okay, very good. By the way, guys, attackers would also use this, right? To basically understand what kind of things you are typing. So if your password tends to be something that's easily rememberable, it's also more amenable to attacks, because if an attacker uses hidden Markov models to break your password, if your password has English substrings, the attacker would find those passwords faster. So there's a good reason for passwords to be like QJLK9743, right? Great, because this kind of breaks your, the probability of these substrings in your hidden Markov model state transition diagrams are very, very low, right? But at the same time, the trade-off is it's hard to remember this password, okay? So this is the sweet spot with all these password breaking business. Okay, very good. So now that you have the state transition, you have this likelihood, you have this distribution. Now what you're doing, your state transition is doing is you're saying, okay, my S1, it's likely to be A, B, C, D, and W is one possibility. And given your initial measurements being close to W, you say, okay, W is a very much a possibility, and the other possibility is Q, and the other possibility is maybe A. These are strong possibilities. And ESX or ESXZ are lower possibilities because this distance is larger, right? So you start from there, and let's look at W. Once you do W, the next one being the next one being J, this is number 2. This is number 2. So the next one being J, you say, the measurement says that this J is very likely, but my dictionary says W and J, W and maybe this is J over here, this value is very, very small. So I say, okay, this probability was high over here, but this WJ, this probability Pij is very small. So at this point, I have low belief that the user is trying to write something which is WJ something. Okay, WI, the second one was also close to I. So it's a WI, and then you look at W and some I in your matrix, and you say, this probability is pretty high because W and I, there are lots of words that are WI. You say, very good, let's continue doing that. And then you say WIR because third can be R. And you say WIR, that word, there are not too many words like that. Weird is WEIRD, right? WIR, there are not that many. Again, your belief goes down along this trajectory, right? Essentially, you're saying this trajectory, I was very confident initially. I was also pretty confident now, but suddenly my confidence goes down. Like, that's what you're doing. So then you say, okay, the third one could be R. But the third one could be E too. Okay. If the third one is E, then WIE, there are still possibilities. WIE, wield, is a word, right? So you said WIE, and then you say, okay, what is the next one? Fourth one, L. Oh, that's pretty good. WIEL matches, agrees very well with the motion model and with the measurements. WIEL. Awesome. Your confidence is very high. He said, go for it, go for it. This word is very likely. And then the fifth measurement comes in, right? 5. Oh my goodness, D is here, right? Your confidence goes down. Oh, maybe not, right? So then you say, okay, similarly, WUR maybe is also not good. So you say, okay, let's look at the Q version of it. Let's start from Q and see whether the trajectory starts from Q and what all trajectories agree with both measurement and model. QJ, unlikely. QI, unlikely. QU, okay, that looks pretty good. Q, 1 is Q and 2 is U. Not bad. 2 being U, possible. But the motion model is saying that's very possible. And then you say, okay, third one, possible that it's E, possible that it's R, because third one could be E or R. So you say, okay, R, E, and you say, oh, Q, U, R. I don't think there's a word like that. I don't know. I think there isn't a word like that. Your confidence on this trajectory goes down. But you say Q, U, E, oh, that's not bad. That's entirely possible. L, okay, great. QUL is doing very good. And now the fifth measurement comes in. You say, okay, the fifth measurement is over here, and maybe this is L. That is pretty good. That means that gives you quell. Fifth measurement being M is also likely, but quem, QUELM, there is no word like that. So that probability again goes down. This probability is pretty high. D, quelled, there's no such word, goes down. Quelk, no such word, goes down. So you say, okay, this one is a likely word. Let me put it in the suggestion. Okay. By the way, there is the third measurement after U. The third measurement after U, if you take A into account, yeah, third is a little bit away. But if you take A into account, then fifth measurement is pretty close to M, right? So if you take this trajectory where third one you assign to A, then ALM, oh, that's a good trajectory. So maybe we should write this one as well. Haha. So if I say QUA, Q was high, U was even higher, A went down a little bit, but L got higher, M got even higher, right? This is my arrow shows my confidence level, right? Quell was good, quam is good. So I put quell, quam, while, when, all of them on my suggestions.
I have a question.
Yeah.
It seems like in this quam example, you're changing the values of the S, whatever, I guess S3 here, based on future measurements. So like here, RE is like part of S3, right? I guess.
Which one is part of S3?
R and E.
Yeah, R and E, yeah.
And then you go forward into, I guess, S5, and based on those measurements, you're changing S3.
No, right? I'm not changing S3. Adil, I'm not changing S3. Remember, okay. I definitely don't want to confuse you with this one. I will keep every S1 will have A, B, C, D, everything. I should have.
No, I mean the values of the things in S3, not just like what's in S3. So like maybe say you're typing Q U E, and then on S3 I guess for A, like you have like a really low probability.
Correct.
But then you go to L, and then you go to like M, I guess.
I'm not going to change this probability after I go to M.
Okay.
Okay. So my Q probability is pretty high from S1, right? From first measurement, M1. Okay. Right. My Q probability is pretty good, right?
Yeah, sure.
Then once my Q probability is good, my U probability goes up quite high because Q followed by U, my motion model says very much possible, very high probability. And my measurement of 2 says that I'm reasonably close to U. So my probability goes higher. But then third measurement, QUA, actually QUA, if you look at the words that start with QU, many of those words may have A in it. Quasi, quam, quadrant, right? So my motion model is saying good for A, but my measurement is saying, nah.
Oh, okay. So S is coming from your transition matrix only, right?
Say that again.
Is your value for A in S3, is that coming from the transition?
No, it's a combination of both measurement and transition matrix.
Okay.
So my measurement is saying good. Sorry, my transition matrix is saying very good. QUA is very likely.
Okay.
But my measurement is saying no. The third finger tap is pretty far away from A. So my confidence that had gone up at U now goes down, gets dampened a little bit. So it goes down now. But then we say, okay, don't worry, let's keep going and see what happens. And then when you go to L, they say, oh, okay, if that was, although A, my confidence got dampened, but now that I see L, I feel like there are a lot of words that are QUAL, right? So my confidence again increases. And then I say, okay, the last one is M with reasonable probability, measurement-wise. And language-wise, QUALM is a great word. It's a pretty frequent word. Therefore, at that last minute, at the last point, my confidence goes up pretty high.
Okay.
Right? So Quell might also have a good confidence. Sorry. Quell might also have a good confidence. Quam might also have a good confidence. So the keyboard takes the words that have the highest confidence, maybe the top 3 words, and puts it in the suggestion. Every word has some confidence in it. It's just that QUELD has a very small confidence. That's all. Okay, good. So this decodes to Quell or Quam or I don't know, even while, so forth. You take the top K and you put them in your keyboard. Okay. I hope this gives you more clarity on HMMs, because we're not only doing it for motion tracking, there are various other ways to actually use the same ideas. Okay. And a quick one in speech recognition. Can someone tell me how you can now think of speech recognition? You think of speech recognition the following way. MK is your measurement. So you record the human speech, and now your signal looks like that. A, K, B, R, H, right? That's the signal that you've gotten, right? And the possible states SK equals that might be some signal like that. B, that might be some signal like that. K, that might be some signal like that. and so on. These are called phonemes. Basically, these are the building blocks for all the pronunciations you make. Okay? So you've gotten a measurement. This is your state space. All the hypotheses that you have. Adil, this is likelihood or posterior?
Likelihood?
This is likelihood. Very good.
Okay.
Good. Right? So you make this. And then you also get PS2 SK plus 1 given SK. This one you get from where?
The state transition matrix.
State
right?
transition. Where do you get the state transition diagram?
Prior knowledge?
You take data from people speaking, and from that you figure out what is the probability that a b is followed by a. So you say abnormal, or you say, that's a b followed by a. What is the probability of j followed by a k? So hardly, there's no word like that. Kaja, there's no word like that. So you say, okay, so probability of sk plus 1 equals j given sk equals k, or j and k, that probability is 0. Right? Maybe in a different language, in Swahili, there are words that are kaja, right? Then for that word, for that language, you will update your state transition probability. Right? Okay, again, you have the same thing. You apply hidden Markov model. You start decoding what word is being spoken. Okay, many applications. Very good. So that's all we'll talk about in this case. And now we will, now we will move on to one more application in arm gesture tracking using IMUs. And we have some videos that might be interesting, but I will move on only if you have no questions here. No questions?
Just kind of unrelated. What were you actually typing
Say that again.
in the word model that you had? What were you actually typing?
Oh, I just made this up.
Oh, okay.
I started with quam in my mind. Okay. Then I said, okay, I'm going to move the measurements around to confuse you enough so that I wanted to push you towards quell. And I didn't think of whelm. I wanted to push you towards quell and while and quell, right? So I moved around those locations so that you have confusion between these words. Right? But I started off with quam. Yeah. Very good.
I have a question about that speech recognition example that you gave, application that we talked about.
Right.
So for the state transition matrix, like the second probability here, is there like a phoneme dictionary or something like that that we can use instead of recording people to?
There is speech people have developed this dictionary where they have taken every pronounceable word and broken up into phonemes. Right? Actually, hey, don't our dictionaries have that too? There is a pronunciation for every word now, actually, right?
Mm-hmm.
Right. So it would say Robin, and it would say Ra-o-ba-i-n, right? So you have these phonemes, the sequence of phonemes for every word laid out. So you can go to the English dictionary and even pull out the pronunciation, the correct pronunciations for all of them. And they would be in terms of the phonemes.
Got it.
Right. So you have a phoneme dictionary essentially. Very good. Yeah, we are going to talk about acoustics after this, right? We are talking about mobile computing as an area, mobile computing algorithms. By the way, guys, you are very much doing machine learning without us calling it machine learning at this point, okay? So we are going to look at acoustics after this. So we are going to handle some of those phonemes and some other noise cancellation, some things related to speech as well. So stay tuned. Okay, very good. Now, next I'm going to talk about let me share my screen. Haha. There's a message. Let me read the chat messages once. Yeah, this method is actually very powerful. Yeah. I wonder if tonal languages are harder. Utkarsh, what are tonal languages?
Like Chinese?
So they're harder because?
Because like a single sound can be pronounced in many different
Sure. Oh yeah,
fluctuations.
Sure, definitely. I think once there are different ways of pronunciating a word, I think now you have to do more signal processing because maybe the amplitude of the signal matters, right? So I'm sure, I'm not an expert in speech, but I have a feeling that if the emphasis, right? If those things are going to matter, it's another ball game. Yes. Transition matrix is huge. And not only that, transition matrix now becomes also a function of the signal quality, right? Because if your signal has noise, it might sound like sha, but it's actually sha, right? So all of those problems are there. Great. So another application of HMM, today is a day of applications, no math, okay? So, but I hope you don't hate math anymore. So this is an application where we want to basically track our arm from the IMU on a wristwatch, okay? And using hidden Markov models, where we will set up the motion model, we'll set up the measurements, okay? And you understand this very well now. This is one of our papers, one of my students wrote this. He's in Facebook research labs right now, but he did this work in 2017 or 16 maybe. Great. You can all see Tom Cruise. Yeah, good. Okay. So understanding human arm motion, that's the goal. There are two ways of understanding this problem. One is, how is the arm moving? And the other is, what is the meaning of this motion? In other words, how is the arm moving means, what is the trajectory of this arm? The 3D trajectory. It means it's a vector of XYZ values. What is the meaning of this motion means that for this vector, what is the person really doing? It's the semantic meaning. So what is the meaning of the motion? This is often called the problem of gesture recognition, such as, oh, the person is jogging and therefore the hands are moving like that. Okay. The person is driving, therefore the hands are moving like that. Right? The person is drinking tea, so therefore the hands are moving like that. So I do not really care about exactly what is the trajectory of the hand or the arm. I care about what is the human understandable action the person is doing. Does that make sense? Right? So gesture recognition is often amenable to machine learning because you do these kind of motions and you label that data as drinking tea. You do this kind of motion and you label the data as jogging. Right? You do this kind of motion, you label the data as smoking. Right? And the machine learning algorithm does not give you what is the trajectory of the hand. Right? Given a data, I just want to classify it as gestures. So there are lots of words in gesture recognition in literature. Now, how is the arm moving? This is often called posture tracking. And this is more of a motion tracking problem that we care about, where we really want to get the XYZ coordinates of your hand over time or of your arm over time. So applications of this might be sports analytics. In fact, we have been engaged in sports analytics quite a lot. you want to understand where the person is doing something wrong in terms of shooting the basketball, right? You really want to know, oh, at the time when he's releasing the ball, his wrist is actually undergoing a gyroscope theta change. That's the problem that's happening, right? You want to measure these kinds of precise motion patterns. This is not a problem of gesture recognition, right? Machine learning will immediately say this guy is actually shooting basketballs. Okay? But this is where you need trajectories. And there are many other places where you need trajectories, such as you want to use your arms to do as a remote for the TV. You want to do that, your TV will swipe. You want to do that, you want to do that, your TV will zoom out, right? You want to do that, the TV will zoom in. Healthcare, you had an accident and you have lost some of your arm motion. And over time, using physiotherapy, you are recovering. How do you measure how well you're recovering, right? You might be able to say, oh, last week, I was only able to bend my arm this much. This week, I'm able to bend it more. Right? So I need fine-grained analysis of what my arm's motion looks like, the 3D trajectory, maybe of my wrist, of my elbow, and so forth. Gaming is another example. I want to do this wearing an IMU on my hand. By the way, AR, VR is very much into this, where I want to do certain things in VR with my arms, and I exactly need to know where my arm is. So this is the kind of problem we are interested in. So the question is, can we track arm postures, and particularly with a smartwatch alone? Good. So what is inside a smartwatch? You all know by now what is an accelerometer, what is a gyroscope, what is a compass. You know all of this very well. So what do we need to track? If we want to track an arm, what do we need to do? Okay. So this paper, by the way, you'll read this paper. Oh, let me make a quick announcement now that I remember. The next MP has been released. That is about motion tracking, IMU-based motion tracking. And also there's a paper to review, which is this paper that we are talking about, which is called ArmTrack, this paper, okay? So both are listed on the course webpage, so please look at that. Okay, good. So what do we need to track the whole arm? Okay. In this paper, we bring down the problem to tracking 3 things. 1, the elbow location. 2, the wrist location. And 3, the wrist rotation. These are the 3 things we want to track. And we are saying that if we can track these 3 things, we can track the whole arm. Okay. There's one assumption we are making over here, which is I am going to track the position of the arm, the posture of the arm, with respect to my shoulder, which means the shoulder is the origin 0, 0, 0, and I'm going to understand where my elbow is, where my wrist is, and what my wrist orientation is, everything with respect to the shoulder, right? So which means if I'm lying down and if I'm straight, I'm not going to be able to differentiate between those two, right? If I have my arm like this, and I'm lying down versus I'm straight, the arm posture will still be the same. Because with respect to my shoulder, there's no difference. Make sense? Very good. So all of this I'm going to do with respect to my shoulder. If I start moving, this ArmTrack paper is not able to solve it. Because then the shoulder itself is starting to move with respect to the global coordinate frame. Okay, I still want to say, if I start moving, actually forget it. Just assume that the shoulder is static and now I want to move my hands. There's a further paper to be written, which is a very difficult work, difficult research, and maybe you'll take this up in your grad school or if you go to some research job, which is even while I'm walking and I'm moving my arms, can I tell how my arm is moving? right? So I'm playing basketball, I'm moving, my shoulder is moving, and then I do this shot. Can you tell me how my arm moved? This paper cannot solve this problem. Because if you're moving your shoulder, the measurement that you make in your IMU is going to be a function of both your torso movement and your arm movement, right? And it is hard to separate out which one is the torso movement and which one is the arm movement. Make sense? So this paper is only saying, I'll keep my shoulder fixed and I'm going to move my arm only. And can you measure my arm? Can you estimate my arm? So what do we need to track? Let's look at the unknowns. Again, I hope you get into this, after this course, you get into this mentality. Any problem thrown at you, grad school, industry, job, research labs, wherever, even life, what are the unknowns that I care about, right? And do I have enough equations to solve those unknowns? You should get into that modality of thinking. So first unknown is your elbow. And that elbow, the location of that elbow has two unknowns. Why? Why not three unknowns? Because I want to measure everything in 3D. So why is the elbow location only two unknowns? Someone?
The distance away from your shoulder is fixed.
Correct. Okay. So your elbow can only move on the surface of a sphere with your shoulder at the center. Correct. Jian Hao has the right point. Another way of saying it, the length of the upper arm is fixed. Very good. So you have two unknowns. So never feel, oh, just because I have to do 3D tracking, therefore it's three unknowns. Because remember, your motion is constrained to the surface of the sphere and the surface is 2D. Very good. The next unknown I have is the wrist location. That is also 2D. Why is that 2D? Oh, because that wrist location, if I know the elbow location, then that wrist location is actually on a 2D surface around with the elbow as the center of that sphere. Very good. The third one is wrist orientation. And we have only one unknown. Why, guys? Why is there only one unknown? Rotation is typically three-dimensional. So only why one? Okay, which axis is this rotation? If you look at your hands, which axis is your wrist rotating? You can do this, right? That's the rotation we care about. So which is the axis? This is the axis, right? You're rotating around that axis. Yeah, I want all of you to kind of do it with, as you listen to the talk, right? So this is the axis. What are the other axes? This axis, right? Right? But you know, this axis, your watch is not going to measure, right? Because your watch is over here. Your watch is not going to measure that, right? What is the other axis? This. What is the other axis? This. Can you rotate your wrist around this axis?
Painfully, maybe.
How? Really?
If you break it.
If you break it, there'll be more unknowns in the paper, in your solution, okay? For sure, okay? But this whole project is possible because you cannot break your hands, which means your hands, your skeleton constrains the degrees of freedom, which means your motion model is constrained, right? If you are a puppet, like those straw puppets or those balloon puppets, then it's hard to solve. If you put a smartwatch on the wrist of that puppet, you won't be able to solve it because the motion model is very weak. So these are the 5 unknowns that you need to solve. Okay? Don't think of this as, oh, elbow location 3D, wrist location 3D, wrist orientation 3D. No. I hope you see how we are going towards a motion model, right? Life has a lot of domain knowledge, dictionaries. In the auto edit, auto correct case, we had dictionaries. In this case, we have this skeleton which constrains what you can do. The way the dictionary constrains what English word you can write. Very good. So smartwatch contains these things, and the posture is essentially elbow location, wrist rotation. The question is, can we use these sensors that we have to solve the posture problem? That's the question we have at hand. Okay, so experiment 1, let's double integrate and do dead reckoning. Okay. So we have gyroscope. You know how to single integrate gyroscope, get orientation. You know how to use accelerometer and compass to get orientation. You get you use some complementary filter, and then you do sensor fusion and you get wrist orientation. That's your wrist orientation. And then once you get your wrist orientation, you project your smartwatch into the global reference frame. Once you project, your smartwatch's reference system is now aligned with the global reference frame. Now you subtract gravity, because you know gravity is now acting in the negative y direction. That gives you the linear acceleration of motion. From that, you single integrate, you get velocity. You single integrate, you get wrist location. Okay? This is one way of estimating the wrist location and wrist orientation. We have not talked about elbow yet. Cool. This is something that you already know. This is exactly what we talked about when we talked about dead reckoning with IMU. These are results from actual wrist orientation. Not too bad. This is under the assumption that the smartwatch or the arm comes to a pause periodically. Okay. As a result of that, whenever it comes to a pause, you can compute the orientation using accelerometer and compass. Guys, do you remember those things? Accelerometer gives you the gravity anchor, compass gives you the magnetic north anchor, and you can compute the orientation if your object is static, if your IMU is static. Right? Otherwise, if the object is moving, you have to do gyroscope integration to get your orientation. So wrist orientation is not too bad, but look at what happens with wrist location. Y-axis is the error. In the previous graph, wrist orientation, y-axis was the error, but the error was in degrees. For wrist location, the y-axis is the error in location in meters. And it's very bad because this is where you're double integrating accelerometer. So double integration won't work. So if you just try to do wrist location tracking, forget it. Wrist orientation, maybe. So then what do you do? Now, here is another thought. Say, okay, look, I have 5 unknowns, right? How many equations do I have? How many measurements do I have, guys? I have wrist gyroscope. I have measurements from my IMU at my wrist. So I have accelerometer 3, gyroscope 3, magnetometer 3. So I have 9 measurements and 5 degrees of freedom, but 5 unknowns. I should be able to solve it. What is the catch? The catch is the 9 measurements that you have are not measurements of location. Gyroscope is a measurement of change. Accelerometer is a measurement of change. Right? Acceleration is a measurement of change. double derivative of displacement, right? Acceleration is double derivative of displacement. So remember, if you want to understand what gyroscope gives you, it's a function of the current orientation and the previous orientation. Similarly, accelerometer gives you, what accelerometer gives you is a function of the current orientation and current location, previous location, and previous location. So this is a case where your measurement is not an immediate equation that will help you solve your unknown, right? Your measurement is a function of the previous and previous location. As a result, what you really have is not 5 unknowns, but 5 current unknowns, 5 previous unknowns, and 5 previous unknowns. All of them together is what is embedded in the gyroscope, accelerometer, compass data. So actually, to connect your measurements to your unknowns, you need to model the whole system as 15 unknowns. Because unfortunately, your measurement is a function of the previous state. If your wristwatch had a very nice, very precise GPS, then you don't have this problem, because that will exactly give you location. But your wristwatch has IMU, which gives you inertial measurement, and inertial measurement is change. And 15 variables is a very high dimensional space. All the hidden Markov models we were doing thus far, SK was one variable, right? Is one location where the user is. 15 variables means SK has to be a vector of 15 values. That's a huge pain. Again, you don't have to understand this fully. Even if you get roughly what is going on, the paper will help. And even after the paper, my goal is to give you enough so that if you encounter this problem in future, you would know where to start and you would have all the tools and ammunitions ready to jump in and basically iron out all the details. Very good. So you need to find a way to reduce the search space, because 15-dimensional, tracking a SK vector of 15 dimensions is very, very hard. Okay. So here is the key observation that this paper makes. This paper says, imagine your arm is in some posture, and from that you know the orientation of your wrist, orientation of the smartwatch, of the IMU. If you know the orientation, then the possible postures of your arm are very few. Let me say that again. This paper is saying, look, your arm motion is not a fluid motion that it can do any random thing. In fact, if I can measure your orientation of your wrist correctly, the number of possible postures of your arm which has that same orientation is very, very few. And therefore, if I get the orientation of my IMU, the space of possibilities where your arm can be is very small. Let me ask you to do this for me. If you do your arm like this, why don't you guys do this with me? Your arm is like that. Now, try to move your arm around such that the orientation of the wrist does not change. If you do this, the orientation of your wrist has changed. If you do this, the orientation of your wrist has changed. The only thing you can do is potentially this. You agree? If you do that, your orientation has also changed. Right? The only thing you can do is, actually you might be able to do that a little bit. So if you want to move your arms like that, you need to move your elbow a little bit to keep the orientation of your wrist fixed. right? If you just make this a rigid body and you move up, then your wrist orientation will change, right? Because your wrist is now not oriented in the same way as this, right? So if you do that, you need to do that. You need to move this part of the arm, which is possible, right? But there are many things that you cannot do because your wrist orientation will change. Can you give me one posture of your arm for which you cannot change, at which any change of the posture will change the wrist orientation? Okay, let me say that once again. Give me a posture of your arm, and for that posture, let's say the wrist orientation is O. Now, any changes to that posture will change O. Can you think of such a posture? For example, let's say this posture. My orientation of my wrist is like that. I can move this in. My orientation is changing, but I can do that, right? So my posture of my arm is changing, but my orientation is remaining the same, right? Look at this. My orientation of my wrist is like that, but I can move my arm like this. I cannot move arbitrarily, but at least I have some motion for that fixed posture. Now give me a posture in which the orientation, give me a posture for which if you change the posture a little bit, the orientation will change. Can you think of a posture like that?
I'm not sure if I'm understanding the question correctly, but would rotating your wrist change the orientation, or
which one? Which one?
Rotating your wrist?
Yeah, rotating your, remember, right? Imagine a 3D coordinate frame that is attached to your wrist. Rotating your wrist will rotate this one as well, right? Right? This whole thing will rotate together, right? Because remember, your 3D orientation of your IMU is the mismatch between your IMU's local reference frame with the global reference frame, right? So if you rotate your wrist, your coordinate frame that is attached to the IMU will also change. So is there any posture in which you cannot move your hand anymore because any movement will change the orientation of the wrist?
Wouldn't straight out do it? Because even if you try to bring it back in, your arm kind of, you can't bring it back in straight.
Perfect, exactly. You cannot bring it back in straight, right? Your arm orientation, if you move it closer to you, your arm orientation will change, right? No, but Alex, I can potentially think of a movement where as I'm bending my elbow, I am also lowering my lower arm. I'm also compensating for my elbow movement by changing my lower arm so that my wrist orientation stays fixed. I can think of such a motion though. Yeah, right. So my upper arm is moving and my lower arm is compensating for the movement so that the wrist orientation stays the same. Here is the one that I'm thinking about. Okay, this is my orientation of the wrist. Now make a motion which will keep the wrist orientation fixed. You cannot. Right? You make this motion, the wrist orientation has changed. You make this motion, the wrist orientation has changed. So when my wrist orientation is like that, right, in this direction, this is my 3D coordinate frame. Hey, what does this say? If you figure out that your wrist's 3D coordinate frame is this, you immediately know the whole arm posture. Right? So in other words, the human skeleton and the muscles and the ligaments and the tissues have created this dictionary or this constraint model in which if you know a little bit of information, You have to know the right information. But once you know that right information, the whole space of possibilities becomes constrained. So here is an animation of where the user is moving his arm so that the wrist orientation remains upwards. The orientation is not changing. And these are all the motions you can make. But you cannot make any other motions. So now if you look at where the elbow, okay, forearm is pointing upward, palm facing towards yourself. That's the motion. Oops, sorry. So these are all the locations that the elbow can go to. Right? You can, this is what your skeleton prescribes or dictates. And the wrist location is also another point cloud where the wrist can go to. Right? So now you can see this for different orientations of the wrist. When the wrist is oriented in this way, the red point cloud is where the elbow can go. You can keep that wrist orientation like that, and you can move your elbow and your lower arm to keep the wrist orientation like that. Then the elbow can only go to these red points. Right? So guys, this is where I'm coming towards. Given the wrist orientation, the locations of the elbows are now constrained. This is my motion model, right? These are my motion models. These are my motion models. These are my motion models. So for a fixed wrist orientation, arm posture space, and remember space we learned in linear algebra, the arm posture space is small. This is promising as we already estimate wrist orientation reasonably well. Wrist orientation we can do well. We have gravity, we have magnetic north, and we have gyroscope. We can combine all of them to do wrist orientation. But how can we derive this point cloud for each wrist orientation? Right? This red and blue, red and green point cloud. We need to derive that, right? Because that's our dictionary, right? And we do not have a way to derive that one. So this is where you can use, you can basically model it using trigonometry, where you can say, look, my elbow location is a function of θ1 and θ2. Look at θ1 and θ2 on the shoulder. θ1 is my this motion. θ2 is my this motion. Right? And from human motion models, I can figure out that θ1, the maximum range of θ1 is maybe 270 degrees, right? You cannot do 360, right? This is the max you can go to, right? So the maximum of θ1 is 270 degrees. Maximum of θ2, how much, guys? Roughly?
Like 100 degrees,
100 degrees, 110 degrees. Okay. So you can model this from human motion models. And there are medical science literature of what is the value of θ1, θ2. Wrist location you can model. Wrist orientation you can model. Of course, wrist orientation will be a function of θ1, θ2, θ3, θ4, θ5. θ4 is basically this motion. How much is the range of θ4, guys? Roughly?
like 160 or 170.
170, right. So you have these models. This tells you for a given orientation, what is your red point cloud, green point cloud. Very much true. Now I'm going to basically measure my wrist orientation and from that try to infer wrist location, elbow location. Okay. So here is one animation where you see the point cloud changing based on the orientation of the wrist. You see certain orientations have a large point cloud. Let me play that again. Again, the wrist orientation is going to change. And for that given wrist orientation, the right side strawman is showing how big is the point cloud. Wait. See, some wrist orientations have pretty big point clouds. Right? Good. So how large are the point clouds? The point clouds are not equal for every wrist orientation, right, guys? Right? The point clouds are going to be different. So how large are they? So what we did was we took the area of the red part, the area of the red point cloud, and divided by the area of the sphere. That is how large it is. Right? And we looked at that distribution for all possible orientations of the wrist. And this is what the distribution looks like. On average, the point cloud is 8% or 9% of that sphere. Right? Of that whole sphere that the wrist can be at, or the elbow can be at, the elbow can only be within 9% of that whole sphere. Is that a good news or a bad news? I think at 11:34 everything is bad news, but I'll stop right very in a minute. Is that good news or bad news? 9%?
I think that's good news, right?
Good news, exactly.
Because we are constraining it.
Exactly.
Like,
you're constraining it to 9%. This is like saying in the dictionary, if you know that there is a word that starts with A, the next alphabet is only going to be 9% of A to Z. So if it starts with A, the next alphabet is not going to be all possibilities. It's only 9% of A to Z. That's pretty good, right? You've constrained it a lot, which is good news. Right? So since they're small, so here is one idea. Don't do any fancy hidden Markov model. Just take the average of that point cloud. Does that make sense? Because once you know the wrist orientation, you know the point cloud for the elbow. By the way, guys, point cloud is all the possible locations at which the elbow can be given that wrist location, given that wrist orientation. So one approximate thing to do is, hey, don't bother about any of those hidden Markov model business. Just take the average of that red point cloud and say that is where your elbow is. That itself would give you some good results because that point cloud is so small. If you do that, your error of your elbow and wrist is decent, around 12 centimeters, 1 feet. So imagine you can move your hand wherever, but just by computing your wrist orientation, you can tell your elbow location with a 1 feet error. Not bad, right? You've done nothing. You've not even used any Viterbi, any transition probability matrix, nothing. But there are problems because there are some orientations in which the point cloud is pretty large. And one of them is this. Right? Orientation is fixed, but I can be in all these postures for that fixed orientation. Okay? That is where things become tricky, and that is what we are going to look at next class, and we are going to continue quickly with SLAM and particle filter and then move into acoustics. Okay? But I hope you see how everything is coming towards hidden Markov models is that these red point clouds are changing based on the orientation of how the arm is moving. Right? And you now apply hidden Markov model. You get measurements from your IMU, you have motion models, you combine. Okay. Questions? Questions?
since we have different point clouds for different elbow locations, would from a hidden Markov,
Deep, slow down. We have different
Sorry.
point clouds for different wrist orientations.
sorry, wrist, wrist orientations,
Right.
would the state spaces for the hidden Markov model be different for each orientation? Like the S1, S2, the state spaces?
Okay, I understand your question. We will say that the state space for the elbow location is the full 2D sphere around my shoulder. What is the state space? Every location that the elbow can take, right? That's the state space, right? So we're going to say the state space for my elbow is the whole 2D sphere around my, with my shoulder as the center. Agree?
Mm-hmm.
But we will say, look, in this state space, only the red point cloud has high probability and everything else is 0.
Got it.
Right? This is the same as saying, when you observe a word Q, the following alphabet can never be J. Right? That means once you've seen Q, the following alphabet has state space of A, B, C, D, E, F, G, H, everything till Z. But U is very likely, so high probability, but J, K following Q, that state space, those probabilities are 0. So it's exactly the same. Q is your orientation of the wrist, and elbow state space is, given that you see the orientation of the wrist, the elbow state space only lies in that red point cloud, everything else is 0. The same way, once you've seen a Q, J, K, L, P, all of those are 0. Only U, and I don't know if there's any other alphabet after Q, maybe there are, only those are the non-zero probability. Those are the point cloud. So in other words, for Q, U is in that red point cloud, everything else is 0. Very good. That's a good question. Yeah. Other questions?
I know there was this question in the chat, and I was also wondering the same thing, is where do these I guess point clouds come from? Are they determined geometrically from just like the possibilities that?
Exactly. So there are multiple ways of doing it. One is you get a person in your lab. Okay. Hey, have you seen these Hollywood movies in which, you know this movie Avatar, right?
Yeah.
Right? So, or even these animation movies that are realistic, they actually get a person, they put stickers on the entire body, and there are IR cameras that shine light and get the reflections from these stickers and can precisely understand how the hands and body is moving, right? So from those, they can actually, in the movies, what they do is they say, okay, the lion is going to run, or Avatar, that guy is going to run. So they make the actor run, and exactly what that motion is, they copy that motion onto the animated character, right? So they exactly know what that motion looks like. So once if you can do the same thing, you can now say, for this orientation of the wrist, where all were the elbows, right? You can get that red point cloud from real data. The other thing you can do is completely geometrically. You can say, okay, I know that this range is only 180 degrees. This range is 270 degrees. I can do the math. Basically, it will be geometry. And I can say, for this orientation, the elbow cannot be beyond these set of points. Then you can do LU sine theta, LU cos theta. It's going to be trigonometry, basically. Right? The only thing you need to know is what is the range of mobility of a skeleton, of a human skeleton. Right? So you can do it geometrically. So that's how you bring in your point cloud, the red and green point cloud. Good question. Okay. Anything else? Okay, class is over. So I will again see you on Monday. And Monday, we are going to finish off this part, maybe in another 15, 20 minutes. And then we will jump into acoustics. Okay, great. I'll see you on Monday then. And start off on your MPs and your reviews. Okay, see you guys.
Thank you.
Bye.
Thank you.